So, hi everyone, everyone present here and everyone who will be watching the video later on. We will be having this particular session of Cues to Cognition, as I call it, to discuss very basic analysis of, I guess, ERP analysis. Today I'll be getting that. I mean, I prepared myself for both, ERP and as well as frequency analysis. But whatever is comfortable with everybody, we can actually have a poll and go ahead with that. I'll start with EEGLab. I'll open it up and we can just get the data pre-processed here. In case anybody has a question, in case anybody thinks that we should move on to something else like frequency analysis, you please you're free to put it in the chat box. And if in case I'm not able to look at the chat box, please feel free to open your mic and answer and speak up. So this is the way I run EEGLab. I hope EEGLab, installation is very easy, so I'm not going to discuss that. Also, this session is not a teaching session because EEGLab is very commonly used, and I just wanted to do something productive on a Sunday afternoon, and that's why I thought let's just get together and discuss some analysis. For those of you who do not know analysis, it's a great start because I've shared the data, which is the scrape data, but it's good. It's a good data to look into to start with. For those of you who know things, and if I'm doing a mistake here, and or maybe if I can, develop on my steps further here, you can please tell me, and we can discuss things so that we only improve together. So. This is EEGLab window, and this is how we import data here. So I'm going to import my demo data that I've shared with you all. I'll start with ERP analysis. So I'm going into the ERP folder, and I'm getting the dataset 1. I'm importing it here, the full dataset. I'm naming it as D1, dataset 1. All right. Now, I'm going to do some basic steps of pre-processing here. I'll start with adding channel locations here. So this is the default file location which is installed with EEGLab, and this is put in here, like this is default, so we don't change anything here. Now the channel locations are imported. Now I'm going to start with, okay, so first let's discuss the data. How does it look like? Because this does not give us a very beautiful picture of what it is here, but still there are numbers. Next step would be to look at how the data looks like, right? The channel, number of channels is 64, as you can see here. This is frames per epoch. This depends upon the sampling rate here. The sampling rate is 500 Hertz. Events are 157, so there are many events. Before going ahead, I would like to discuss the data set first, what it is actually. The data set is actually a flanker task, which I did years back. And it basically has congruent and incongruent stimuli, but divided into two categories. One is left category, there are arrows in the flankers task. So the arrows, one category of arrows face towards the left side, whether it's congruent or incongruent, that you can make out. If you're not able to understand what I'm saying, please go and search for flankers task. You will definitely understand what I'm trying to say. You just have to see two types of images, stimuli types, congruent and incongruent. Okay. Give me a second. I want to change the view here. Again, it's not. Oh, shit. Alrighty. Okay. Anyway. So the flankers task is composed of two types of stimuli, congruent and incongruent, and we have two categories of these two stimuli as well, and that I can show you here in this picture. So incongruent is composed of right incongruent and left incongruent. So R1 and R2. R1 is for odd, that is left, and R2 is for even, that is right. And similarly for congruent, R3 is for left facing arrows and R4 is for right facing arrows. Now, if the person gave correct answer, that was marked by R9. If it was an incorrect answer, that was marked by R10. So here we will be mainly talking about R1, R2, R3, and R4. These four basic stimuli types, because that's what we are going to work with. But for now, you can see that there is only one epoch because we have not segmented the data. So the data is in one continuous form. That means it's one epoch. And event are 157. So we can divide it into 157 segments. But again, here are, so like 157 segments of events also include R10 and R9, and we are not going to work with them. Only these four events, R1, R2, R3, and R4, right? Channel locations, since we have added them here, so it's yes. ICA weights, we have not given the ICA components here, so it's not here right now. And reference is not known for this particular file, but it's FCZ for this particular data file. We have the data time period as well, 0 to 153. So yeah, it was a very basic overview of the data. This is the real data, and this very bad signal comes from a mystoid channel, which is FT8, and we can actually remove that later. But this is a nice way to just preview the whole data first. So I'll be skipping the segments. So the data otherwise looks very clean, as in it has very nice wavy structure. These kind of segments can be removed by just marking them and then clicking reject. We'll not do it right now because we haven't filtered the data yet. So we'll just first give it a chance by filtering it, and actually some people prefer cleaning the data first and then go ahead with filtering. But since this is an event based study, we can actually do with the filtering first and then go ahead with the cleaning part later. So basically, in other major frequency type of studies, it's important to look at the each segment of the data, because then you will be using a continuous sort of data, and here you will be using segment sort of data. So it's okay to first filter it and then clean it manually. Anyways, the data looks good. Some segments are bad. We can come back to them later. This is the whole data, and yeah, again, the bad segments are here. So I didn't want to take any, the online databases because they are pretty clean usually, and it's not very interesting to work with them. So these kind of data sets, which are real world, they really seem to be teaching us a lot of things, because errors actually teach you a major part of the learning, rather than the idealistic data sets. So yeah, so I will start with pre-processing now. We'll first change the sampling rate. It's 500 by default. We will go ahead with 250 because that makes it very easy to process the data, and it happens very fast. So you can see the iterations are happening here. It was very quick. So it's now done, and the file is renamed as D1 resampled. Now we'll filter the data. So I was going through an article today, and with that article, I understood that there are some problems that might occur with the data if you, band pass your data, put in the lower and the higher band pass filter together. So it's better that you first band pass filter it with a higher pass and then put the lower pass later. So I'm going to do that right now, but maybe for understanding that, we have to go into the depth of the signal processing, which I'm struggling to. So maybe if any of you understood why this might happen, and you can also go through some of the articles written for EEGLab filtering, you'll get the idea there. So maybe we can discuss that and understand why this must be happening, that putting both the passes together creates a mess around here. So I used 40 hertz filter, and yeah, it's now filtered. So I'll change it to filtered. So after each step, we can have a look into the data. It looks better to me at least. So now we choose the lower edge, right? Okay, excuse me for So we have to go look at the data. Yeah, looks fine, right? Now is the time when we interpolate electrodes, but maybe we can re-reference it first so that there are no channels missing when we are re-referencing it. The data is re-referenced. Well, so before interpolating, obviously I'll have to look what channels are not good for me. And I hope you understood why we re-reference the data. And if not, please read an article for that. If not, if you don't understand, we can discuss it later. So in the last session, we very elaboratively discussed why we re-reference. That's why I'm not taking it up here today, not owing to the time. Only FT8 is acting bad here. And one other channel was acting bad previously, but I think that's cleaned up here right now. So we'll go ahead and remove interpolate FT8 from the data. Okay, well, the channel that appeared bad is now interpolated, and it's working fine now for us, right? And one of these channels is also acting weird, but I guess we can try to avoid its seriousness because it's acting very weird for at very specific intervals, and that can be removed as well. So no need to interpolate the whole channel. The data looks good to me. So see, very basic steps that we have to follow are pretty much done now, or whatever is required for an ERP analysis. So we changed the sampling rate, we filtered the data, we re-referenced it, and we interpolated the channels which were acting weird. But before all this, we added the channel locations, right? These were very basic steps which were done in EEGLab. Now I'm going to use ERPLab, which is one of the plugins that come with EEGLab. You can go and download it using the links, whatever is available online for ERPLab. And then you can add it, the file that you've downloaded, in the plugin folder in EEGLab file that is there, right? So, yeah, before moving on to the epoching part, I'll just briefly discuss one thing that I would like to highlight. So we are using here FIR filters, and FIR is finite response, right? And there's another thing which is called infinite filters, right? So there's a difference between the two. Now, this is for IIR filters and this is for FIR filters. You can say, so very basic, in very basic terms, not in very signal processing types terms, because I'm not great at it. So it gives me no right to discuss in those terms. It's just that if you are using finite filters, they bind your uh, limit to a particular number that you're giving it, right? But in case you're using an infinite filter, that will actually take you to an extended phase, a time phase, a time delay, which is not what you chose. So it's like if you're taking off 1 to 40 hertz of a filter, a bandpass filter, that might give you a phase delay of per se 44, 45 hertz, right? It will take it to that extent. But if you are using finite filters, then it will definitely give you only 1 to 40 hertz. It might go up to plus zero point 0.5, but that's a different thing. But this finite filters will give you a specific range of filtering. So that's why there's a difference between FIR and IIR. And I'm telling you this difference because when I used to work with brain vision analyzer, that gives you an IIR, and that gives you the power to change the order of the phase delay that you will be using. So this is one thing to remember whenever you're using a filter, and in whatever software and whatever coding platform you're using, you have to take a note of that particular thing, right? So I'll quickly look at the time. Okay, yeah, it's not that much, right? So we'll jump on to ERP lab now. And this also gives you some basic steps to cover for a continuous EEG set. But since we have completed all the basic analysis in EEG lab, we will only be focusing on segmentation and ERP plotting using ERP lab. Okay? So we have to first create an EEG event list that may or may not be different for all the database data sets that you're using. So yeah, there is a path that is already here that I had already fixed here, but I'll again tell you how to do that. Not a big deal. Since I'm using all the files that are here, I'll choose this folder and I ask it to save it here. So since I had already created a file, it is asking me to replace it, but yeah, that will not happen with you. And yeah, an event list has been created. Next, you assign bins. Now this bin lister file that you have to create is a tricky part, although it's not that tricky. Uh, this is the format that we use to create a bin lister file. And this is nothing, it's just the bins that you're going to have in your data set further on based on the events that you already have. So we had different event types, right? So in this particular photo, if you see, there are R1, R2, R3, R4, and Rn, R10. Although I told you that we'll be working with only these 4 events, so I created a list which had only these 4 event types. This is the way you write the event type, and this is the way you write what that event type means and what is the label that you're going to use in the data set further. So this is bin 1, bin 2, bin 3, bin 4, and that is how I have explained them here. I hope I've done that right. We can always cross check it. So event 1 is left incongruent, event 2 is right incongruent, event 3 is left congruent, and event 4 is right congruent. So that's how I've created this bin lister file. This is the format that it reads it in. And I've given it the path to this file and then I run. So I've assigned the bins to this particular file, right? So this file is renamed. Now extract bin based epochs. I'm giving it the time period that I require for it, minus 100 before the event for the baseline correction and 1000 after the event for the whole analysis. Since this is flankers and though I had given 3000 milliseconds for the person to react, but whatever components appear, they are more prominently appear, they more prominently appear in 1000 millisecond, and that is the time that is required for the whole analysis. So I'll only take 1000 millisecond and not further that. But if you require, in-depth analysis, you can always go ahead and take more time. So the last thing we did was extract bin-based epochs. So we have the epochs now. The next thing we do is compute averaged ERPs. So this has all the details, the default things are fine, and we go ahead and run it. We have to give it a name to the ERP dataset that will be created. So this is for the dataset 1, so I give it as D1. Now you can see the D1 ERP set has been created. Cool. So we have a database and we have all the epochs that are present there as averaged segments. Okay. So now we can plot them. So you can choose what bins you want to plot, and I'm going to only plot the left ones right now, left incongruent versus right versus left congruent. For what channels? I'm going to only take the Z channels, the midline channel, FZ, EZ, OZ, PZ, and POZ or CPZ. And then I don't think anything else is left. There are ways you can choose to plot them, like topographic. MATLAB and MATLAB 2 give you some specific, you know, template to plot them in different ways, but I'm going to go with classic ERP right now. And yeah, I think everything is fine for us. You can go into the depth of these default details, whatever is present here, they are perfectly fine for us. And then we go and plot them. We just hope that they look fine, and they do. In case they don't, we can go back to the data, although this part. So when these data sets are plotted, these things are plotted, you have to double click on those little boxes and then they zoom out, zoom in, right? So this is how they look like right now. Although they look clean, pretty cute, but if you're not satisfied, since I'm not satisfied with how they are looking, we can go back to the data set here. And this is a way to check. It's although it's a long way to check whether your data is fine or not, but again, it's always important to keep a check on how your data is, the quality of the data is, and then only you have to plot it. So right, the re-reference data. That was the latest data that we were working before we plotted, before we epoched them. And yeah, this is one way to look at the data if there are any anomalies in the data, and we can go ahead and remove it manually. So for example, here, this part, this can be removed by clicking on reject. And then if you go ahead to the to plot the data, you'll see that that part was removed. Since it was removed, we cannot make out if it was removed. But yeah, this is one way to keep a check that your data looks clean and there is no big, disastrous change there. So anyway, I think it gave you a good idea of how to do ERP analysis with ERPLab, and you can do it on your own, and we can also come back and discuss things here. Now, so if anybody has a question regarding this, because I chose all the very basic steps to do here, and since I wanted to record this session, I wanted to keep it very short as well, and that's why I'm done here, and I've tried to inculcate all the important points that I know, and maybe I am missing some points, but again, I can always make another video, and we can hold another session so that we get to meet again, and yeah, we get to learn more. So yeah, this is it. And for the ERP analysis, I'll just stop the recording here.